Hi everyone. Today I will present my final project 2 in the Applied Regression Analysis course. My name is Zelei Cheng, and let's go to the first part, Introduction. First, I will introduce the background. Here is the topic we need to investigate. It is related to concrete compressive stress. It is the capacity of a material or structure to withstand loads tending to reduce size. It varies from 17 MPa to even greater than 70 MPa for certain applications. So the original research question is how to predict the concrete compressive strength. Previous research has been done using machine learning methods, such as artificial neural networks, to predict concrete compressive strength. But my project is related to linear regression model. So here is my research question. The first one is independently develop a linear regression model to predict the concrete compressive strength. The second is to discuss the role of predictors. Is there a particular predictor standing out as the most promising one? Why or why not? The data is listed on Blackboard. The header of the file looks as below. In the next part, I will introduce the dataset characteristic. So here we have one response variable named concrete compressive strength. We need to predict the response variable. And here are some potential explanatory variables listed as below. The sample size is 500. And here is some basic descriptions of variables. As we can see that the variable named concrete compressive strength, which is marked as yellow, is the one we need to predict. And the variables marked as blue is the potential variables we need to make sure whether they have influence on prediction. The detailed screening process is as below. In the following part, I will identify some outliers and influential points after using remedy methods. Some of the influential points will be dropped from the original dataset. Also, according to the result of best subset algorithms, some variables will not be considered in the final model. So the next part, in the third part, I will perform some preliminary analysis. So first, I will introduce the data set, the CSV file, to the R Markdown. And here is how I write the code. And here, I first do scatter plots. We need to identify whether there is a multicollinearity problem here, right? So here, from the scatter plot, we cannot see very clearly if there is any multicollinearity problem. So I compute the correlation matrix and plot the correlation matrix here. And we can see here, there might be some problems between X4 and X5. And maybe some weaker multicollinearity problem between X4 and X7. But it may not be very serious. From the scatter plot and the correlation plot, there might be a multicollinearity problem between X4 and X5 and X4 and X7, as we have seen before. To begin with, we create a naive linear model to investigate the relation between Y and X1, X2, X3, X4, X5, X6, X7, X8. So here we draw the residual plots to see if anything happened. And here we can see there may exist nonlinearship in X8, the fitted values and maybe in x5, x2. And here in the first part, we will build our model and perform diagnosis and validate our final model. So let's talk about our first order model that investigates the relationship between y and x1, x2, x3, x4, x5, x6, x7, x8. Through preliminary analysis, there may exist non-linear linear relationship and the multicollinearity problem. Further diagnosis is required. So here is the summary of our first model. We can see that the adjusted R squared is not very high. It is only 0.6211. And maybe some remedy methods can be performed to improve the adjusted R squared. And here is the ANOVA table of our first model. The sum of squares is a bit large. So here, to begin with, we use F-test to test the following hypothesis. The HO is all beta k is equal to 0. The HA is not all beta k is equal to 0. So we can compute the test statistic Fs. The result is 103.235, which is larger than F 0.958, 491. Therefore, we reject H0, which means that there should be some beta k not equal to 0. Then we perform a BF test for constant virus. The HO is defined as follows. Residuals have constant virus, so HA can be defined as residuals have non-constant virus. So here is the R code for BF test. The result is difference is significantly significant. It's statistically significant, which means that we should reject HO. The virus is not constant. And then we perform Shapiro test for normality. HO is data follows normal distribution versus HA, data violates from normal distribution. So from the R code, we can see that there might be some problem with normality. And also from the normal QQ plot, you can see that the normality assumption might be violated. And then we prepare a partial regression plot for each of the predictor variables. Here, the plot suggests that the regression relationship in the fitted regression function is inappropriate for x6 and x7. x6 and x7 may provide no useful information for our prediction. I should not transfer any of the predictor to better fit a linear model since there is no nonlinear pattern in the added variable plots. So first, I do box-Cox transformation. And I found that the lambda star is equal to 0.7575758. So here I transform y to TFY. The formula is as the slide shows. So now let's consider the transformed model. That is, investigate the relationship between TFY and x1, x2, x3, x4, x5, x6, x7, x8. So to begin with, we will see the model summary. Here we can see the t-test result of the explanatory variables. We can see from here, x6 and x7 can be dropped from our model. And here is another table of our second model. through the formal model summary, X7 and X6 might be dropped. Let's do best subset analysis to find which explanatory variable might be useful. So here, from the result of the best subset algorithms, here is some criteria we need to consider when we want to select the best model. The adjusted R squared need to be as high as possible. CP need to be small and near to P. AICP need to be as small as possible. SPCP need also be as small as possible. The press P need to be as small as possible. So here we select the 6 model. We can see if in this selected model, X6 and X7 are dropped, as we analyzed before. So here is our new model. Investigate the linear relationship between TFY and X1, X2, X3, X4, X5, X8. So this is the summary of the model based on the best subset algorithm. So here the explanatory variables are limited to X1, X2, X3, X4, X5, X8. And we will perform model diagonals in the further step. This is another table of our third model. Here, we need to investigate if there is any outlier or influential points. So here are 3 concepts tightly related to outliers and influential points. The first one is studentized dilated residuals, which is to identify the Y outliers. The second is height matrix leverage values, which is related to identify X outliers. The third one is Cook's distance, which is used to identify influential points. So to begin with, we plot an influential plot. You can see there might be some influential points and outliers as identified in the figure. So from the chart, we can further discuss any outliers or influential points. The first is stewed rice with the Bartholini procedure. A case is potentially an outlier if Ti is bigger than 7.9. So from the chart, we cannot see any possible cases that are identified as underlying with regard to its Y value. The second is the height value. A case is possibly an outlier if HRI is bigger than 2, the inspection of H, which is 0.028. There are 5 cases are identified as outlying with regard to its X value. The third one is Cook's distance. A case is considered an influential point if Di is larger than, so here we mainly consider 2 cases. The first is major influence, that denotes as a 50% line, and the moderate influence, which indicates 20%. There are no potential influential points. So here is our first remedy method. Remove some cases. Remove the cases 31, 137, 160, 173, 210. So here we create a new data file with 495 data points. The model is TFY follows X1, X2, X3, X4, X5, and X8. So to begin with, we plot the residual plots. From the plot, we can see that maybe a higher model of X8 may need to be included. And here we can see that the adjusted R square is not much improved although we have to do Box-Gauss transformation. And the BF test still shows that the difference is statistically significant. The model still have non-constant variance. And the Shapiro test shows that it violates from normality. So here we can see that we may need some advanced remedy method. For the non-constant variance, we may need to think about using WLS remedy method. But the result is that the non-constant variance problem and the non-normative problem still exist, even when we use WLS remedy method. So the BF test results shows that difference is statistically significant. And the Shapiro test result shows that it violates from normality. So here, as we analyzed the residual plots, we may need to consider adding a second order element to the regression model. So here we just add an x8 squared element to the model. So here we plot the model summary. We can see that the adjusted R squared is 0.74. It has been improved. And from the residual plots, the nonlinear shape has been improved. And the BF test still shows that there might exist a non-constant virus problem, but we can perform some remedy method on this model. The Shapiro test shows that the normality assumption is not violated. So here are some potential influential points. As we have analyzed before, the non-constant variance problem still exists when we consider using the WLS method. The non-normality problem occurs when using WLS method. As we can see that the only violation is a non-constant variance. So we consider WLS method. From the PF test, the result is that the constant variance assumption is violated. And the normality assumption is also violated. So we remove the potential influence points again. So here is the new model based on data excluding influential points and outliers. The residual plots still have some problem. And the BF test shows that the constant variance assumption is violated. And the Shapiro test shows that the normality assumption is not violated. So here again, we consider the WLS method. The weighted model passes the BF test and the Shapiro test. So first, let's see the model summary. The adjusted R squared is 0.7769, which has been improved. And here is the ANOVA table. The residual plots has been improved compared with the original one, because you can see that from the y-axis, I think that it has a good fit. And the BF test tells us that difference is not statistically significant. It means that the constant virus assumption is not violated. And from the Shapiro test, at the significant level of 0.05, the normality assumption is not violated. And here we plot the normal QQ plot. So finally, we get a regression model with a transformation TFY is equal to y raised to 0.050755758. And here we use an advanced remedy method named the WLS method, which is a weighted model. So finally, we get our final model. To begin with, I need to discuss the potential issues found in the preliminary analysis and solutions. The first problem is multicollinearity problem. So to solve this issue, I first analyze the correlation matrix to find out there might be a multicollinearity problem in X4 and X5 and X4 and X7. And then use best subset algorithm to select a subset of predictors. The predictors that have a multicollinearity issue are excluded. The second issue is the nonlinearship problem. So here we include a second order element, i.e. x8 squared. The third problem is non-constant variance and violation from normality. So here we use box-Cox transformation and the WLS methods. The fourth problem is outliers and influential points. So we just remove some outliers and influential points. And here are some answers to my research questions. The first research question is to independently develop a linear regression model to predict the concrete compressive strength. So this is a model we construct as our final model. It is a weighted model, and it uses box-Cox transformation. The concrete compressive strength has relationship with cement, blast furnace slag, fly ash, water, superplasticizer, and age. The second research question is to discuss the role of predictors. Is there a particular predictor standing out as the most promising one? Why or why not? From our formal analysis, we can see that there is a particular predictor standing out as the most promising one, which is age. From our final model, the introduction of second order of age item has made a significant effect in the model performance. Age, that is X8, in our model, leverages great importance in predicting the concrete compressive strength. As the age increases, the strength will decrease. Compare this linear model method to whatever method that has been used in the reference. So for example, in our project, that is neural network, we will discuss the pros and cons of both methods. The pros of the neural network is that the neural network can use nonlinear function approximation to accurately describe the relationship between the response variable and the explanatory variables. But our linear regression method can efficiently compute the predicted response variables without much time, which will indicate the cons of the neural network. It is time consuming. And we cannot explicitly see the importance of each predictor, since it is a non-linear function approximation, and we cannot directly see the importance of each predictor. The cons of the linear regression method is that the accuracy of the linear regression method is lower than the neural network method. So here comes our conclusion. In this project, I developed a second-order linear relationship model with advanced remedy method. The regression model passes the BF test and the Shapiro test Compared with the original first-order model, the adjusted R squared has been improved. So that's all. Thank you for your listening.